we're going to do something a little bit more complicated with this notebook. So I showed you a notebook that was sort of a working notebook, right? This is the thing that I do, and I'm writing code and I'm testing things out. This is the notebook that we use when we're trying to impress people, right? So you can use notebooks for different things. And I didn't write this notebook. This was written by a woman named Sarah Bird. She's a half-time Continuum employee. She mostly works for a nonprofit that focuses on issues that I can't recall now. But Sarah Bird is the author of this. And this is an example of bokeh, which is a sort of visualization and plotting library in Python. And you'll see sort of why you would use it instead of something like matplotlib in the future. And the important thing about this is this. We're going to go through about maybe 50 or 60 lines of code. But hopefully sort of the end result will be worth it and neat and interesting. And if not, then I didn't do it right. So don't worry too much about the Python syntax here. This is good form. Instead of doing from bokeh import star, right, there's a from bokeh import the specific things that you need. This is namespace control. This is something that you have very good control over in Python. C++ has something similar to this in the namespaces, which is nice. C and Fortran have relatively little concept of this. There's static data in C and global exports, but it's actually relatively hard to control your namespaces, and embedded namespaces are just about impossible. OK. So this is namespacing. It's a helpful thing. This is some text explaining what we're going to do. Is anybody familiar with Hans Rosling and Gapminder? OK. Well, for those of you who aren't, you'll be doubly impressed because you haven't seen the data or how it's been presented yet either. Maybe you've seen the TED Talk. OK. We're going to take a look at fertility, life expectancy, population, and region all over time, right? So generally in scientific computing or high-performance computing, we're happy when we get performance or efficiency versus number of processors, right? We only think in terms of maybe one or two variables at once, at least in terms of how we sort of think about or visualize things. Here we're going to take about 5 different things and we're going to visualize them simultaneously. So imagine that instead of just doing our performance plots, instead of only controlling one variable, we had a couple of other different things that we were looking at, right? Performance method, resolution, all of these things you can visualize, but you wouldn't use something like a basic line chart or a bar chart. You would use something like a scatter plot, or in this case, what's called a bubble chart. So we're going to use a bubble chart, and we're going to get more information out, and we're going to make it sort of visual and exciting, and something that you can show a funding panel, or your PI, or somebody else that you want to get excited about the work that you're doing. So most of this is basically just getting the data into a format that bokeh wants, right? Basically these column data sources. And then there's a lot of building up the plot. And this is a programmatic plot. And the nice thing about programmatically generated plots is what? They're reproducible, right? We know exactly how this plot is generated. And if we want to tweak something, we can. We'll end up with sort of a usable thing instead of somebody handing me a PDF or something and I have no idea how they generated it. This, we know exactly how the data came in, what the transformations were done to it. And we can tweak this if we wanted to. We can also check to make sure that fertility is being mapped to fertility and not to something else. OK? So this is the last little bit. This is the key of interactivity. If you want a plot to change, or you want something to change in a widget or some other interface, when somebody moves it or toggles it, you have to write a function called a callback function, or a hook. And basically, that hook gets called every time somebody interfaces or modifies something in your user interface. So in this case, the only hook here is this slider, right? And the slider has some basic annotation here just saying where it's going to start and end. And then people call the slider, and our function gets called. And of course, our function should be relatively quick when we replot, because if it isn't, people will drag their slider around and then not see much. that's the HTML output. And this is a visualization, again, of fertility and life expectancy over time for various countries. So what you have here is sort of the classic concept of first world and third world, where these countries have this high life expectancy, and they also tend to have a low fertility rate. And then you have countries with a low life expectancy. So these are life expectancy was somewhere between 40 years of age and 50 years of age. And as time progresses, you're going to watch, and it's easy to see various countries. Each of these bubbles is a country. The size of the country is its population. The size of the bubble and the color is where it's coming from. What you're going to see is these countries move over, right, into this side of the plot, where the fertility rate's going down and the life expectancy is going up. And we're controlling that with this slider here, right? And of course, we've got this nice visualization of the year in the background. And so we can just walk through this. And there's no computations that are being done, right? The computation has been done in the past, right? What we're doing here is we're just visualizing all of this data that's been loaded up. So again, this is something that you could create, right, in an afternoon with an IPython notebook if you had some output that you really wanted to like really wow somebody with. You can turn this into a web page, and you could even upload this somewhere. And somebody could take this data, they can work with it. So this is an example of a static visualization. This isn't touching any real computations or data in the background. There's another tool we have called Bokeh Server, where you can actually connect it to live data sources. And you could do something really wild, like talk to a supercomputer and monitor things on the supercomputer or jobs that we're running. So there's a lot of potential over here. I wanted to show this to you because I think it's really cool, right? This is something that could be in your hands today. This is a free tool. It's all open source. So the notebook itself, Bokeh the library, you could download this example, and you could do something similar with it and adapt it to with your own data. Okay. So we're going to talk about building code. This is also an excuse to try out the Continuum template. So, okay. Building software is hard. And we're going to talk about this twice. We're going to talk about it in the context of the C, C++, Fortran world on supercomputers. We're going to talk about it again from the general Python ecosystem. Because there are lessons from how Python has dealt with packaging that are applicable to your own development and deployment and sharing your own code. People tend to work with stacks of code now instead of single libraries of code or a single executable, right? It's no longer the case that you get handed a pile of source code and it has no external dependencies. If you're using these codes, right, you're not relying just on your own code that you've written. You're relying on these other libraries that somebody else has written. Maybe that person is trustworthy. Maybe they're more trustworthy than you. Maybe they're less trustworthy than you. But the idea is that this is becoming more and more complicated. This is true. This code is not where it used to be. Okay? So programming, I think of it as just simply another form of writing. And so when you're using other people's code, you're basically taking their chapters and putting it in your book. There's two types of writing. There's interpreted versus compiled. Everybody's comfortable with the differences between these two, right? So when something is interpreted, it enters some sort of intermediate state. Usually there's some sort of bytecode or something else where it's read, but it's not exactly machine code yet. Whereas when compiled, it goes all the way to machine code. These are the different tools that sit between, right? So a compiler goes from what we think of as like C code or Fortran code to these .o files, this object code. You have a linker, right? And that's responsible. That goes from these sort of individual .o files into a shared object library, a .so, or a static executable. Maybe it's a.out by default. Maybe it's something else. Okay. And then this assembler goes from assembly into machine code. And then there's this archiver. Archive is a very, very simple thing, right? So AR, right? It used to be like tar, where it would pack and unpack files into tar archives or archives, these .a things. But now the only thing anybody uses Archiver for is creating static libraries. It's just a collection of these .o files in basically a tar archive. That's all this sort of static library is. Shared libraries are far more complex. The level of complexity that goes from a static library to a shared library is much, much more than you think. A shared library is a form of ELF binary, just like an executable is. And this is something that's designed to be picked up and read by an ELF loader. Not that kind of ELF. Okay? So the ELF executable and link format has a header, right, where it talks about what type of CPU it will run on, what compatibility it has. It has an endianness set in there so that just to double protect you against screwing something up. And then it's composed of a bunch of these sort of runtime segments. Okay? And then there's link load time information, which are sections. And then there's the program data itself, right? So the sections are something that that the loader runs or looks at when it's bringing the program into memory, whereas the segments are things that are only sort of brought in at runtime when the code is actually executing. So if I'm trying to link against a shared library, I look at sections. Okay? Or when I'm running the program or starting it up, it goes into sections. Other things go into segments. And there are table headers, and there are tables for navigating into these. Okay? And then there's a bunch of tools that people use to work on them, right? So just the file command will identify an ELF binary, right? NM allows you to read symbols off of ELF binaries or libraries. LDD will inspect the link and the load time information. Readup will pull most of the information out of this header for you. Objdump is similar to NM, and then it gives you the objects out. And then patchelf, which is my favorite, allows you to modify it. So if for some reason you want to modify an ELF executable or library after it's been built, patchelf is the tool. Okay. This is the basic taxonomy of the various types of programming languages. Starting all the way sort of from the most low level, machine language is what we talk about. When we're actually reading something on a computer, it has basically just the lowest level instructions. These usually have a direct mapping to an assembly language, right? So this is represented as 0xxff, and this will be something like move or pop or add-I or any of these other sort of instructions that represent a single instruction that at least a human might have a chance of understanding. Okay. Above these two, slightly more is object code, which is the output of compiling, say, a function or a piece of source code like a code module like C or Fortran. So it's important to understand how these things are named so that when you work on a tool that operates on them, you know which piece of the stack you're on or in. So when you're building something, say, in a makefile, if something is a piece of object code, you understand that it's in an intermediate state. It's not yet a program. It's something that's ready to be put into a program. Okay. When we talk about these high-level languages and these scripting languages, high-level languages are trying to get you as far away from assembly language and machine language as possible. 30 or 40 years ago, C was considered a high-level language because you weren't writing in machine language anymore. Nowadays, most people don't consider C to be a high-level language. It's down. We think of it as really close to machine language. It's just a slightly more portable version of machine language. Then finally, a scripting language is something that was designed originally to control other applications, right? It was something where you sat at a terminal and you say, OK, take this program and do this, and then take this program and do this. So it wasn't designed to sort of run directly. It was designed to run programs. Nowadays, there's sort of a mix between these two things, right? There are scripting languages that can generate object code or assembly code, and there are sort of low-level languages that really want to be high-level. I'm looking at you, C++. OK. This final bits, relocatable, right? Means something different when you were talking about a set of code that you're trying to give to somebody else and when you're trying to compile something. Anybody ever gotten an error where they tried to link against something and it told you that you needed to recompile with fpic? Yeah, OK. So when you create an object file, there's one very important sort of set of instructions that you can give to the compiler, a very important switch that happens here. The first intention is that the code is going into a static executable or archive. And in that case, all of the locations are effectively hard-coded. So anytime the compiler generates a jump instruction or a branch, anything where there's a change in where to go for data or code, where it's referring to itself, there's an indirection that's put in if it's dynamic or if pic has been enabled, this sort of portable or relocatable code. If it's not there, then everything is hard-coded in the static case. So when the compiler later on, and you try to link this sort of non-portable code with a portable archive, or turn it into a dynamic library, the compiler will say, you can't do this because you didn't have fpic turned on. It's generally safe to turn fpic on. It's just usually sometimes a little bit less efficient. For example, on Apple, whenever you use any of their compilers, fpic is turned on by default. That's why most people don't even know what that flag is on OS X. Whereas on Linux, it's not on by default. And in a lot of supercomputing environments, for sure, the builders of the machines and the maintainers do everything possible to hide shared libraries from you, because they can be very difficult to work with for a couple of reasons. But one of them is this extra trick of having to have that fpic flag on. OK, we know what an executable is. And again, the shared object file is this sort of funny thing, right? This .so library usually only comes in as a runtime link or as a you can describe it as a compile time link, but generally it doesn't get brought in to the executable until runtime. And this can be shared by multiple programs sitting in sort of the load time variant of the library. OK. Probably the most important thing to understand about building software, or one of the most important things, this is maybe one of my 5 maxims, is everything you do when you're trying to build software is implicit until you yourself make it explicit. So when I type make, for example, right, the compiler runs. And I can make a very, very simple make file, right, that has just one line that says grab every object file in this directory and turn it into an executable file. Or I can even say, hey, just grab all the source files in this directory and turn it into an executable file. Now, what's implicit there is all of the files. But what might be explicit is that, oh, well, it's actually only these source files. Now, if I just say grab, let's say I'm working on a C++ code or a C code, and I say grab every C source code in this directory. If any of these C source code files changes, you got to rebuild it. Am I safe? Do I have any implicit dependencies in there? If I just do, program depends on star.c, am I covered? Header files. Header files. That's everybody's great nightmare, right? Because header files, A, can come from the system. But B, if you don't explicitly say, well, for this C file, it depends on this header file. If the header file gets changed, you won't rebuild that module because you haven't explicitly said, well, this depends on this header file. So what do you have to do? You could do star.c, star.h, right? But that doesn't really scale, right? So you have to explicitly specify what the header dependencies are for every C file, or you have to run a tool like depmod, right, where the compiler itself can actually run through the code and generate the list of dependencies for you from each of your source files. If you're using something like auto tools, automake does this for you. This is one of the things that the auto tools suite can do for you. Okay. But sometimes code itself is not enough, right? So we talk about the C files, we talk about the header files, but those are just your codes, right? That's just your set of source files. If the compiler changes, if the library changes, if your input data changes, you're in trouble. So this is David Donahoe. He's one of the most highly cited statisticians, one of the most highly cited scientists in general. And he's been one of the big proponents for reproducibility. And there was this article, this interview with him was, one of the questions was, well, why are you so highly cited? How did you become so highly cited? And he said, well, I put my code out there. And so we talked earlier about advertising scholarship. Well, people could pick up David's code when they read his papers, and they could both verify that what he was doing, and then they could write some addition or modification to something that he'd written, and then they would cite him. And this is the currency, right? If you want to be an academic or a professor or a tenured research scientist somewhere, you have to collect these citations. And one way to do that is to not only advertise your code by writing papers, right? Or not only advertise your work by writing papers, but make sure that you're capturing the complete software development environment. And as I said, this has gotten harder, right? So 30 years ago, it was very likely that your code lived as a single Fortran source file. 10 years ago, a couple of source files and a makefile was really what you were looking at. And today, it's just gotten worse, right? So people have dependency stacks that can go very, very far. They can require specific versions of compilers. And they're very likely to be using development versions of multiple sort of dependencies. So, and this is progress, right? I mean, well, it's progress in the sense that this is where we have to go. We have to start leveraging more tools. We have to reuse each other's work. And so this problem becomes hard because we have, again, these explicit dependencies, which are easy to describe. But then we have these implicit dependencies that makes things hard. So in terms of reproducibility, you have to understand what things are down here that are making it hard for somebody else to build your code or you to build your code on another machine. So part of understanding how to build code sort of in this reproducible, easy way is really understanding what's down here, right, and what's changing between machines. Because you won't always have the luxury of having full control over this on every system that you go to. You may have to support multiple versions of compilers or libraries. And that flexibility is hampered by the fact that not every library or dependency you use will follow some sort of sane semantic versioning. The semantic versioning, who's not familiar with that? Go ahead and raise your hand. OK. So I'm just going to go ahead and pick on Petsy here, because I love all of those guys, and they produce a really good tool. Petsy did not follow semantic versioning for quite some time. When they moved from version 2.2 to 2.3, and almost any of the other changes in the 2-point line, right, that was an increase in what's called the minor version. The major version is that first number, the 2. The minor version was the 2.2 to 2.3. When you change your minor version, you're only allowed to add things. You're not allowed to break any existing functionality that's available in your tool. Petsy is famous for when they would go up a minor version, they would change all of their interfaces. So they should have gone up a major version, but they would inevitably just go up a minor version. If you are maintaining a library, right, you have functionality that people call. Semantic versioning is a good idea. Or what's even better is putting a 0 in front of your library, right? 0.1, 0.2, your code is technically in beta. You're allowed to break your interfaces if your major version is a 0, right? So if you go from 0.1 to 0.2, you can break every single function in your code, right? You're allowed to do that. So if you know that your code's unstable, don't put a 1 in front of it. That's what that means. After you put that 1 in front of it, you're obligated to either bump major version numbers or preserve existing functionality. OK. Including versus linking, I think we already talked about this. But if you're using header files or this sort of direct injection using includes, that's the -i flag. When you're using links, that's the -l flag. This -r flag on the GCC compiler suite and their sort of compatible things will add the RPath flags for you. I think this does something else with the IBM compilers, but I forget what. Okay. And these links can either be resolved when you build the code, or they're resolved when you run the code. And that depends on whether you're statically or dynamically linking. If you're linking statically, those links are resolved when you build. When you're linking dynamically, they're not actually resolved until you start running the code. And there's this horrible situation where you can dynamically link a code. It theoretically works on the front end of the system, but then when it tries to load or run on the back end, it doesn't work. And this is this sort of horrible complexity of working with these sort of heterogeneous computing architectures where the front end and the compute node don't look the same, or they don't share the same file system. All of these things can lead you astray. And the software and computer architects for these supercomputers do their best to sort of hide these things from you and to make it not visible and not make it horrible. That's why MPI-CC and all of these compiler wrappers exist. Most of the time, all that they are doing is making sure that you're linking to the right location on the file system for when you're running these things on the compute nodes. That is 99% of what's happening in these compiler wrappers. Are there any questions about this? Because cross-compiling is unfortunately still a problem. I don't want to say it's a problem. It's something that you have to deal with on supercomputers.
Is there a trade-off when you decide not to give your code because, for example, right now my development team is debating whether we should ask that you ask for the code rather than just putting it out there. Now, we want to give the code away. We just want to keep control of who has the code. Now, I personally find that a little detrimental to getting it out there, making it popular. I personally think that's going to be detrimental to the purpose. And am I being too cynical when I assume that if we politely ask you to ask us for the code, is that going to turn people down? Are people going to be like, I don't want to ask X? Or is there any benefit to keep any sort of control of who's got your code or not?
This is almost like a panel question. So I'm going to give you my opinion, but there's two other people in this room who have a lot of experience with this, Ancho in particular. Did you hear the question?
No.
OK. The question was, no, it's fine. The question was, should you, when you've intended to release your code, what license are you releasing it under? That's actually.
No, we don't really have a license.
You haven't chosen a license yet. OK. You're intending to release some code. There are multiple developers on it. You own all of the code right now. You own the copyright of all of the code. So you have the complete control over what license to put on it and how you're going to release or distribute this code. Is it being publicly developed? It's probably not, right?
Well, I mean, it's nothing like security. It's nothing like defense. We could literally just release it to everybody.
But the code is not on GitHub, for example, right now.
It's not.
Though. OK. It's being internally developed. And the question is, how do I release the code? And the choices are, do we release the code completely publicly? Do we put it on GitHub? Do we provide whatever public downloads people want? Or do we put some sort of barrier between I have developed this code and I can install this code on installing the code on individual computers? And in supercomputing, there's a large range of sort of levels of access that people have to these codes, right? So there are codes that basically you need a clearance to see or download or use. There are codes where you have to pay somebody. There are commercial licenses on these codes, and they run on supercomputers. There are codes where you have to fill out a long form and sometimes say that you're only using this code for research, and sometimes you only get a binary, and sometimes you get the source code. And then there's codes where you can politely ask, and you tend to get the code. And then sort of the final step, of course, is there are codes where you can just clone it from GitHub. You don't have to ask anybody or do anything. Okay, and it sounds like you're almost all the way on that end of the spectrum, and you're just wondering whether you should put a page in front or not.
I'm basically wondering if I decide to give the code away, no problems, no clearance needed, but I need you to ask me for it so that I can keep track of who's got my code, if it will be detrimental to how popular can it get, how much citations can I get out of my research, because you do want to contribute with the particular community that's trying to tackle the problem you have already tackled.
Yeah.
But personally, I don't care, but some of my people on the research team are like saying, maybe we should keep track of who's got this code.
If you can, I would say put the package on GitHub or Bitbucket or whatever it is, because people are more likely to report issues on your page when you have an issue tracker that people can find and publicly access. They're way more likely to install your tool if they can install it from the command line. And if, for example, you want your tool to be easy to install as a dependency for some other tool, or to go along with sort of a package of other tools, it's much easier to bundle it if there's no sort of license or other thing in place. You're not always going to have this option. If you have the option to do it as open as possible now, I would definitely try and do that.
That's a great point, right? Because if it becomes a dependency for other things, and I impose a restriction that you ask me for the code, but you don't ever distribute it, then people are going to have to, it won't be able to be distributed.
Yeah.
It's that definitely detrimental to amount of citations you can get, and
I think so. I think the other thing that's you should note is that your license file, if you don't license your code now, it becomes harder to license it when you have external contributors. So it's really important to put the license on the code now. And if you put something like a CC BY, or not a CC BY, put like a BSD or an MIT license on the code, and you get approval from your university or your research group to do so, then that protects you as much as anybody else for when other people want to use the code. The majority of local software developers, right, want a tool that's easy to install or is available by default, right, in their system. When I open my computer, I don't want to have to go through a 15-minute install procedure for a tool. I just want to press a button and have it available, right? That's the promise of things like Python and Anaconda. And in order for us to enable that as packagers, we either need to be able to accept the license agreement for you, or there has to be a situation where you don't have to fill out some form or thing like that. Now, the trade-off between how those statistics work, I think, is a really interesting question, right? Can a tool like Anaconda have a profile for you, which has like your name and your email address, and you agree to release that for tools that you install to the teams that are building it? I think that's an active question. I think I'm actually really interested in it, because there's a lot going on right now in terms of how software credit works. I haven't been as active in this sort of this discussion as Anshu has, but there's a lot of ways to think about how people get credited for software development. And I think that there are more solutions than just putting a page up and keeping people from downloading your software. I think you should have it, but I think you should also have a way for people to directly download and install it so that a packager like Continuum can make your software available more easily, or you can make it more easily available.
So can I conclude that there are non-intrusive ways of keeping track of who's got my code while letting them be as free as possible in terms of installing it real quick?
So things like the Python package index will keep track of downloads for you. It'll keep track of weekly downloads. It won't tell you where those downloads are coming from. The same thing with GitHub. If you're maintaining your own page and the software can be downloaded from this page in sort of a binary format, you're going to have a lot of ownership and control in terms of knowing, as long as you use something like Google Analytics or some other tracking tool in your server logs to know what's going on. You have to control the web page at least. So my caution here is that if you have openly licensed code, BSD, MIT, GPL, any of these, and you release your code, you may not be the only person hosting your code. And once you're no longer the only person hosting your code, you basically have to rely on people's goodwill, right? Or some other way that you've contacted or communicated with them to know who's using your code. And in a lot of cases, there are going to be people using your code you don't know, and they don't want you to know that you're using your code. I'll give you a very explicit example. In the Python community, Python is used in high-performance finance. Right? Python is used for data modeling. So there are a number of financial institutions where they have a number of Python developers, and they don't advertise that fact. NumFocus, which is an open source sort of foundation which promotes the use of sort of Python and these high-level languages, receives large donations annually. I have to be very careful because I'm being recorded. We receive large donations from several companies who are promoting the development of Python and the usage of NumPy and these other tools. Do these companies advertise the fact that they use these tools or disclose that in any way to anybody? These operating systems come with incredibly different philosophies for development and ethos for sort of the way that people build stuff and the norms and all of these things. If you come from the Windows world, you will have a concept of a project, right? And it will have a concept of dependencies, and those will be listed in a file. It'll usually be an XML object, or maybe it'll be a JSON object if it's something a little bit more web-like. And that will explicitly list all of the files for you, and you will manage and control this file from a GUI. Once you've sort of established all of your dependencies and your libraries, because Windows has a concept of libraries as well. These are called DLLs, and they behave similarly to dynamic libraries, but they have some very strange and subtle differences to them that you really don't encounter until you've really done some serious development in Windows. But on Unix, there's a very, very different path. And that path is the makefile. All of the big libraries, 99% of the things that comprise your Linux system were built by a makefile. From the libc to the kernel to the compiler, all of these things have a makefile that say, here are the dependencies, here's how to go from the dependencies to the libraries, and how to go from the libraries or other tools to the executables. So a makefile is a giant dependency graph. That's the way to think of it. It's how things are specified. It's also a functional programming language. It's pure, right? These things depend on these things to whatever extent possible. I'm trying to make all of my dependencies explicit. We try to avoid the side effects. Unfortunately, makefiles don't do things like hard code a compiler. Or maybe that's a fortunate thing because you want to use whatever compiler is on your system. But subtle differences in a programming environment, right? If the release of the build system changes, small things can suddenly break in your tools. And so it's helpful, maybe not necessarily to enforce, but at least to capture. And we'll talk about this in a little bit, about how you can do that. OK? So the way that make works is it looks at the targets, the dependencies, right? It constructs this DAG, and then it traverses the DAG and makes sure that the targets are always newer than their dependencies. That's it. If it's older, it's out of date, then it rebuilds the target according to the rules you've specified. Okay. So this is a way to think about that dependency graph. Here's your program. Here's your output at the end. It depends on these two object files. They share a dependency on this header file, right? And they both have their own source files that go in. Okay? And this code on the left corresponds to this makefile on the right. Okay? And the most important thing to understand about makefile is that the targets are the things that are being pointed to. Okay? They're the green things to the left of these colons. And what are the dependencies? Main C, parse C, what else? Main C, parse H, parse C. So are there 3 dependencies in this graph? 5. What are the other dependencies? Main.o and parse.o, right? So target is anything that's pointed to. Dependency is anything that's being pointed from. Okay? All right, maxim number 2 from this slide deck. I think there's only 2 in here. But if you write a good makefile, if you take your time with it, you can actually capture more than just building libraries. You can build applications, and you can actually run experiments. Makefiles are awesome for describing experiments, even with a batch system. Batch system makes it a little bit more horrible, but you can even run experiments with the makefile, right? You can submit jobs, you can monitor their progress, and then when they're done, you can sort of say, ah, and I ran this experiment, and this was the thing that went in to do that, or to create it. So you can capture everything in your system with a makefile. It's sort of the lowest token element for reproducibility. So there's a guy named John Claerbout, who I consider to be the father of scientific reproducibility, or really thinking about reproducible scientific computing. And he came from seismic image analysis. And that's because 50 years ago, if you were an oil man or an oil woman, and you were making this huge investment of tens of millions of dollars or hundreds of millions of dollars to drill a well, it was really important to know what was underneath that well before you started drilling. And so there were all of these people who could promise you all sorts of incredible image analysis results and all of these things. It was, I would say the literature was filled with snake oil salesmen. And so in this particular sort of application domain, it became really important really early to demonstrate your results and be able to reproduce your results with different inputs or different people's code. And so Claerbout and a number of other people underneath him who have worked on a number of these systems like Madagascar focused very early on these tools like Make and Cake. And actually, Claerbout's history going back in the 80s is like, we started with Make because that was what we needed to go from dependencies and source code to the output results. So I think that's a little bit of probably something you didn't think about Make, right, as your core tool for reproducibility. But it very much can be, even on a supercomputer. OK, so Paul said I could write some questions for the final exam. And I've written 2. There's actually one more. Here they are. So you have a makefile with n defined targets and m independent dependent source files. OK, so all of there are n targets and m source files. OK, Make considers a target to be out of date when the timestamp of any of its dependencies are more recent than the target. So what is the minimum number of source files that must be considered when evaluating whether to rebuild a single target? What's the minimum number of dependencies? So what kind of rule? If I had the ability to write any kind of rule, what's the minimum? OK. Now, if this is a properly connected graph, there's no hanging dependencies. How many of them, in the best possible case, would I need to consider if I want to know if I needed to rebuild any of the n targets? Yeah. So if a target has no dependencies, nothing needs to be considered. And there are all sorts of targets. It doesn't actually need to be phony. It can be real. And the makefile will just ensure that that file is there. And if it isn't, it'll say, you said that this file should be here, and I don't know how to make it. But it's a perfectly valid thing to have as long as you want the makefile to ensure that that file exists. That's question number 1. OK. Question number 2, what's the minimum when instead of considering a single target, you have to consider all n? You're not changing your answer because you already said it was m. Does anybody think it's something less than that? Anybody think it's n? This is the best possible case, as long as it's a connected makefile. This is the strength and the weakness of Make, right? So the amount of work Make has to do has everything to do with the bottom of that graph, right? So if you have a number of targets hanging up top and you want to consider all of them, and there are 100,000 dependencies sitting beneath them, Make has to go and evaluate the timestamps of every single one of those. That's not that bad, actually. Yeah?
If you decide it needs to be rebuilt, you don't need to consider anything further, right?
That's true if, for example, you go to the first dependency and it turns out to be newer. But this was the number of files you had to consider, not if you knew what was on the file system itself in terms of their stamps. Yeah, as soon as you encounter one, you can say, oh, it doesn't matter the other 100 dependencies. I'm going to rebuild this. But if you encounter the first 99 and they were all older, then you still have to go to that 100th one. Good question. Good point, though. OK. So make only knows what you tell it, and it's got a number of sort of default variables. But if you don't put something in your make file, it is not going to consider it, right? Timestamps and the outputs of whatever things you look at. And this doesn't affect any of you, but it does scale poorly when you get to really, really, really big builds. But I can name almost no scientific libraries where that's an actual issue. OK. I said I would talk about CMake. This is the slide. Makefiles are used in CMake. I really recommend CMake if you need to build C++ code across 3 operating systems. That is its sweet spot. That's its niche. It's what it's very, very good at. If you're only building on a single operating system or just OS X and Linux, if you can get away with using a plain makefile, that's my recommendation. Most of the time, you don't need auto tools. They're not super horrible to add in. Yeah, if you're using auto tools in a cross-compiled environment, turn on cross-compiling. Fortunately, most supercomputing users are aware of the fact that cross-compiled environments exist and at least make some provision for it. OK?
Do you know a good place to read about how to get GNU build system to work with libraries rather than applications? Because I've looked around to get my API working with GNU build system, and
are you talking about new auto tools, AutoConf, AutoMake, and libtool?
Yeah, I mean, I've seen many examples on how to get your application to include this so that people can download and build more efficiently. But when you're developing a library, I have not seen any good example. Maybe it's my bad, I don't know.
OK. Which specific step are you worried about? Are you worried about building libraries, or are you worried about having your library accessible for other tools?
Building libraries.
Building libraries. So libtool is the piece of the AutoTool stack, which is all about the various horrible ways to make libraries on Unix systems. So it's designed to you say, give me an archive from libtool, and if it's been built correctly, it'll give you shared, static, whatever you need.
And also track dependencies upon which I've built my own library.
libtool can write down the dependencies. And this is where things start getting really, really complicated in terms of what gets tracked by which dynamic libraries, and it's different on each operating system. So if you use static libraries, you never have to worry about it. But if you use dynamic libraries, there's usually some versions of libtool will write down a text file that specify the dependencies. And that's what you're looking for. OK. That's actually more of a packaging question as much as it's anything else. OK. Don't ignore the shell, even when you're writing makefiles. You can have your makefile call shell commands or use subshells. So there's a lot that you can still do from here without diving all the way down into a makefile or to assist or augment your makefile. OK. Any questions about this? OK. Just a couple of basic sort of places to go. I took out my Grace Hopper slide because I didn't think she was going to fit. Grace Hopper's awesome. You should check her out if you don't know who she is or what she's done for high-performance computing and scientific computing. How to write shared libraries is by a very opinionated and cranky Red Hat developer named Ulrich Drepper. It's every single bit of detail you ever needed to know about shared libraries. He also wrote an article about the performance of shared libraries and shared library loading, which is sort of important if you need to deal with things like that. Okay. And then there's links directly in the slides themselves. Does anybody have any questions about what we do in the scientific Python ecosystem in terms of how we write packages, how we test our code, how we do development on GitHub? Yeah, OK, so we have some questions. Think about them now, and I'll try to answer all of them as well as possible before I put on my Continuum hat. OK, you were first.
I was wondering if there, I'm not deeply familiar with Python and its development, but is there any plan to make it possible to do multi-threading and the proper way and not the dumb way?
Okay. Is there any plan to do multi-threading in Python? So there's Python, the language, which doesn't actually specify a requirement for a global interpreter lock. And then there's CPython, the Python implementation in 2 and 3, which uses a fairly simple garbage collector and a C object model, which effectively locks it into, there's a required interpreter lock due to the way Python does garbage collection. So if somebody were to rewrite Python's garbage collector, they could effectively release the interpreter lock. And if you don't need to work with Python's garbage collector, if you're not working or you're not worried about threads accidentally bashing on each other in terms of incrementing or decrementing references to Python objects, you also don't need the interpreter lock. So I would say that 99 times out of 100 in scientific computing, you can release the interpreter lock, and you can have multi-threaded computing exactly the way that you do it in C and Fortran. And I can give you some examples of releasing, we call it releasing the GIL. And I had a really, let me see if that slides in here. I took it out. I didn't think I was going to get a GIL question. Yeah, I took it out. But yes, in the last SciPy conference, everybody was talking about ways to release the GIL. And Continuum has a couple of ways to do it. And there are other ways to do it outside of Continuum. Basically, if you were using Python and you were injected into a C or Fortran library, which is where most of your hot loops tend to be, then when you enter that C or Fortran library, you can release the GIL before you make the function call. And then you can have as many threads as you want using whatever programming model you like. And they can be scheduled in concurrency or concurrent or in parallel. And the other thing on top of that is that Numba, which is the tool that Continuum builds, it's an open source tool, and I'll talk about it a little later, also has a no GIL mode, where basically it can release the GIL in certain types of Python code. OK, thank you. Yes?
So, we have a C++ library, depends on MPI, SDF5, net, CDF, want to write a Python interface. Is Swig still the best way?
OK. Who's the author of Swig? What is David Beasley? Yeah. So David Beasley, I was trying to recall his name earlier, also wrote Bitey, which is the little C extension in Python where you can call C. So David Beasley wrote Swig. He's also kind of a really well-known scientific Python contributor. There was a question asked to him. Maybe I should just navigate to it. Will Bitey ever support C++? No. C++ can bite me. Star. I also wrote Swig and still have C++ scars. So in terms of what's the best way to interface between C++ and anything, the correct answer, as far as I'm concerned, is expose a C interface and then come in, I would say, with Cython. Because Cython makes writing C interfaces to Python really easily. If you're trying to expose an interface for a lot of languages, the C interface will be of general value. That said, I still know people who have done Swig interfaces. So Swig Elemental was recently wrapped. It's a C++. It's a very modern C++ library. And Jack used Swig to do the wrapping, despite us recommending a different approach. This happens. Not everybody follows my advice. But he got it working. So you can still use Swig. Cython is really where it's at. And Cython has some limited C++ support. But I think that if you're using any sort of really advanced C++ features, you want to try and normalize that interface out or try and think about what the C interface should look like first. All of the major projects that have C++ bindings, now we're talking about big projects outside of scientific computing, it's a huge effort to maintain and build them. It's really non-trivial. Yeah?
I want to ask a fundamental question. Should we or should we not use Python in HPC? I mean, is there any good
Yeah, of course you should use Python in high-performance computing. That's why I came.
Is there any good parallelism support to, for example, enable us to run on 5,000 nodes, 5,000 processes?
Yeah. This is so MPI for Pi are straight Python bindings using Cython to MPI. And it's actually trickier to build Python on these systems than it is to build MPI for Pi and that piece of it. And I will say that on an x86 system, Python is a breeze to build. I went through all the pain and scars of getting it working on a Blue Gene P. I have not successfully built Python and its stack on a queue. I know a couple people have done it. But I was sort of getting out of the supercomputing game just as the queues were being dragged into the machine room. So that's where I sort of left my deep involvement with Python and supercomputing. There are a number of people who are building it, using it, and supporting it all across the country. So I should say that I stopped getting involved with IBM systems when the Q came out. And I started working with Cray systems, which are x86. And we built Python across all of those in NumPy. And we were easily running on several thousand nodes. In terms of tens of thousands, hundreds of thousands, you start dealing with some scalability issues with the import mechanism, but there are some workarounds for that. And those will guide you all the way up to 100 or a couple 100,000 if you're dealing with millions of levels of processors or processes. Then you need to start. Then you're in research territory with Python. I don't know of anybody who's run a million node Python job yet.
And I noticed on your download page that the Python 3 is kind of like a second-class citizen. So considering you have a lot of new people coming into Python and getting their first experience, how much longer do you think Python 2 is going to have to be the main stage, and why hasn't Python 3 really taken over for your package?
I can tell you that the two main developers of Conda are huge Python 3 fans, and that Python 3 is a very well-supported environment within Continuum. And we've done a lot of work to move packages over to Python 3 and to make them available. I can't tell you anything else, unfortunately. It's something that we're internally discussing.
Okay.
Yeah. But it's something that you can certainly give us feedback on, because it does help us sort of make decisions about where to put resources like that. Yeah.
You mentioned the make build system, but what do you think about using like Python and just details?
Yeah, we can go into that. Yeah, so Python has its own build system, and it has its own packaging system, and that's something that is very near and dear to my heart. We can talk about it for a while. Are there any other sort of general high-level questions? Is everybody familiar with what Travis is? Does anybody not know what Travis is? OK. I'm going to show you guys Travis before I go into my Continuum slides, which I only have a few minutes for anyway.
Yeah, you might be good. Just, yeah, it's 5 minutes.
Yeah, no, I want to show you guys Travis. I think it's really important. OK. So let's suppose that I am working on a high-performance software package that's written in Python, and that I am considering some code that people have written or suggested for the code. OK. Right. Is anybody here not familiar with the pull request on GitHub? OK. Everybody's familiar with the pull request. So they know what this is. Somebody has created a set of changes. They've committed them to a branch. And then they've decided that they're going to try and get those changes in. OK. One part of this is they describe what they're doing. We can see what their code is. We can see how they changed it. But more importantly than that, OK, I can see how the code was checked or how it was changed and understand how those changes affected the code by running an automatic test for every change that goes into the repository. OK? And so you see that this code was tested against Python 2.7, both in parallel and in serial. Before the pull request hasn't been accepted yet, but before it goes in, everything gets checked. And you can actually go back in your history and see where the code or the build got broken. So all of your tests are automatically run. It's not a manual process. It's an automatic one. That's Travis. That's used on most of the major scientific Python packages, most of the big packages in the ecosystem, NumPy, SciPy, IPython. They all have Travis jobs that are running. Travis is a free service. If you have public, openly developed code, This is another reason to work on GitHub. You get all of these free tools that assist and enable your process if you're willing to work out in the open.